3.4 from the textbook investigates properties of exponential functions. Let's compare three functions: y equals 2 to the power of x, y equals 3 to the power of x, and y equals 5 to the power of x. Now we want to know what these look like, so we first have to make a table of values. And in order to compare them fairly, we want to make sure that each of the table of values has the same x values. To find the y values, you're just going to take your x and substitute it into the exponent. So 2 to the power of negative 2 is actually very similar to 2 to the power of positive 2, which is 4. The only thing is that negative is going to cause the 4 to flip upside down. So instead of 4 over 1, you're going to get the reciprocal, which is 1 over 4. We're going to do the same thing with this guy. Plug it into here. So 3 to the power of negative 2, again, is just 3 to the power of 2. That's 9. Then that negative is going to find the reciprocal. So it's going to flip that 9 upside down, and we get 1 over 9. So I think you're starting to get the point. The last one is 1 over 25. Now after you do that with all of them, you're then going to graph. So we have 2 to the power of x here. It's not as steep as maybe 3 to the power of x. And then even the steepest one, 5 to the power of x. All of them have a common point, and that is the y-intercept. So the y-intercept is 0, 1. And if you think about it, it kind of makes sense because remember that your x value was your exponent. So if you have an exponent of 0, usually you're going to get a y value of 1 because anything to the power of 0 is 1. The only case that that does not work for is if your base was 0. Taking a look at the domain, if you think about it, you can sub in any number into your x, and then you'll pop out a y. So your x actually belongs to all real numbers. You can have any number for x. But if you take a look at your y values, it looks like it's only from, I guess, not even 0, a little bit above 0, all the way up until forever. So your y values are any real number such that y has to be greater than 0. Doesn't look like it goes below the x-axis at all. So I'm thinking that there's probably some sort of an asymptote. In fact, the x-axis is the asymptote, and that is y equals 0. So remember, an asymptote is a line that the curve approaches but never really touches. Now here's a new characteristic, increase and decrease. Well, if we're talking about increase and decrease, we want to take a look at the x values from smallest to largest. So we're moving towards the right-hand side. And then we take a look at what our y does. So it looks like our y values are always increasing in each of these functions. So since y increases, this is an increasing function. The last characteristic is take a look at the base numbers, 2, 3, and 5. The higher the base, the faster the increase is going to happen. So now let's compare three other functions, the reciprocals of those three initial functions. Okay, so we have 1/2 to the power of x, 1/3 to the power of x, and then 1/5 to the power of x. So subbing -3 into here, it's the same as saying 1/2 to the power of 3, so 1 to the power of 3 over 2 to the power of 3, that's 1 over 8. But remember that negative is going to flip that 1 over 8 to become the reciprocal. So the reciprocal of 1 over 8 is just 8. And then if we have -3 as our exponent in here, we're going to have 1 over 27, but then the reciprocal of that, which is 27. So you're starting to get the idea, and again, we just want to fill out the rest of the tables and then graph. So it looks like this time, they're not on this side, they look like they're on this side. So having a different base causes it to kind of flip to a different side. But the 1/2 to the power of x is still less steep than the 1/3 to the power of x, and then also the 1/5 to the power of x. So all of them still have the same y-intercept, and that's what we should expect, because anything, again, to the power of 0 should be 1, except for a base of 0, which we almost never see. They all seem to have the same asymptote again, y equals 0. And then the domain and the range are also the same. Now, in terms of increase and decrease, as x increases from left to right, it looks like the graphs go down, or your y values decrease. So these are decreasing graphs. Okay, now I just want you to understand that we can also apply many of the transformations that we've learned before. So if we decide to then put an a value in front of our equation as a negative, these guys would then flip upside down, and you would get something that looks almost like this. So the reflections still work exactly the same, your stretches and compressions work the same, and then also your translations. Another property would be the base number. So we have 0.5, about 0.3, and 0.2. So it looks like the smaller the base, the faster the decrease. Now that we've graphed everything, that was what, 6 graphs? Let's compare, contrast, and summarize. So how are the graphs from A and B similar? Each of them has the same shape, y-intercepts, and asymptotes. But then how are they different? The first set, so that was the first 3 for graphs of A, those ones were all increase, versus 3 reciprocal graphs, which were the graphs of B, those were all decrease graphs. So then how do the graphs change when you change a whole number base into a fraction between 0 and 1? It reflects over the y-axis. So what that's essentially saying is all of the graphs from A, the increasing graphs, are basically all of the same graphs as B, except for a reflection over the y-axis.